Hi, this is the second video in the series of videos on calorimetry. In this video, we're going to look at an example of an application of calorimetry and see what calorimetry really is. So before we start, let's look at an instrument called the calorimeter. Now, calorimeter is a well-insulated setup. So this is a wooden box. Wood is a very good insulator, and this is wooden lid. And inside we place a copper vessel. We know that copper specific heat capacity is 0.095 calorie per gram per degree Celsius. What this tells us that the copper is really going to absorb very less heat compared to anything else. So it's not going to really absorb too much heat and affect our experiment. And this is a wool, which is a good insulator. Along with this, we have a stirrer to stir the liquid after we put it in, and this is a stand for thermometer. So what we're going to do is we're going to mix two liquids into this, or two materials of different temperatures into this, of A and B. And we're going to study the result. Right, so we know A is, let's say for example, 10 degrees Celsius and B is 50 degrees Celsius. So we want to see what this result is. So we're going to mix them up using the stirrer, and then we're going to use a thermometer to measure the temperature. So that's the whole layout of this instrument called calorimeter. Alright, so let's see the first example that or experiment that we did. In this first experiment, we took 40 ml of water, and in one beaker we measured, this is liquid A, which is 40 ml, and we measured the temperature is 25.6 degrees Celsius, and this is B, which is also 40 ml, and we measured the temperature as 82.6 degrees Celsius. Now when we say 40 ml water is actually 40 grams. So we actually mean 40 grams of water, right? So this is liquid A and this is liquid B. Now what we are going to do is to mix A and B into a calorimeter. So let's mix them up. So for mixing up, first we pour the liquid A into the calorimeter, which is hot, and then B into the calorimeter, and then we stir the liquid and measure the temperature. Now, can we theoretically predict the resultant temperature? Now we know that this is 40 grams water plus 40 grams water, and we have 80 grams water. So the question is, can we predict the resultant temperature? So this can be done using the idea of calorimetry, the principle of calorimetry, and let's see how we can do this. The principle of calorimetry, or method of mixtures, it says the heat lost by the hot body is equal to heat gained by the cold body. So here the hot body is B and the cold body is A. So the way we do this is, let's assume that when we mix A and B, let the resultant, result be T, the result temperature, the result temperature be T. Now if that is the case, then heat lost by the hot body, which is B, will be MB C of the water. The hot body loses, initially it is 82.6 and finally it is T, so it is 82.6 minus T. So we can write this as, or rather let's write this different. Let's write this as M C delta T of B is equal to M C delta T of A. Now what is MA, MB? MB is 40 gram into C of water is 1 gram per degree Celsius per Kelvin, into delta T would be, for B would be 82.6 minus T, because that is a change in the temperature. Now that's equal to 40 grams of A. This is a heat gained by the A, into C would be 1 gram per degree Celsius per Kelvin, into the gain would be from 25.6 to T. So let's say T minus 25.6 is what the gain would be. So we can cancel out a bunch of things, and what you have is 82.6 minus T is equal to T minus 25.6, or 2T equal to 0.2810, or T is approximately or equal to 54.1 degrees Celsius, because we have these temperatures in degrees Celsius, so that'll be these many degrees Celsius. So theoretically, if I mix both these liquids, the resultant temperature should be 54.1 degrees Celsius. Let's see what did we get from the experiment. But surprisingly, we see the temperature that we got is 47.8 degrees Celsius. So the temperature, the resultant temperature of the water was much lesser than what we predicted. Can you pause and think and explain why this is the case? Why is that the resultant temperature is less? Let's look at the anomaly that we just now saw, that theoretically we have 54.1 degrees when we mix using the principle of calorimetry that we have here, heat gained equal to heat lost. But actually we see only 47.8 degrees. So let's explain this anomaly. So what's happening is, so the heat lost by the hot body is by B. So this is delta Q lost, and this is delta Q, the cold water when we mix gains delta Q gain. Now apart from this water which gains some energy, the copper cup here, the copper vessel here also absorbs energy. So there's two delta Q gain. So there's delta Q gain by copper, which we couldn't include earlier, and by the water. And this is delta Q lost is by the water. So let's look at each one of them one by one. Before we do that, let's mark the temperature difference. So for the hot body, the temperature T1 was, so let's mark all of them. So let's mark all of them individually. So let's mark water A plus then copper and equal to, so this both of them have gained of A plus copper equal to loss of B. So that is the principle of calorimetry. All right, so let's look at what happens to A. For A, the initial temperature was 25.6, and let's take the actual values, which is 47.8 that we observed. The T2 is 47.8 degrees. Now, in fact, for copper also, you can safely assume that the temperature was at room temperature. So that's 25.6 degrees Celsius. And T2 was 47.8. That's after mixing, the vessel also gets to that temperature. The loss was for the hot body, which is B. So for this, your T1 was 82.6 degrees Celsius and T2 was equal to 47.8 degrees Celsius. So let's equate these. The QA is MC delta T. So let's say heat gained. So heat gained by A is MC into T2 minus T1, which is 47.8 minus 25.6. This is MA of A plus, which is what A is water, right? MC into T2 minus T1 of copper of, let me call it, instead of copper, let me call it calorimeter, right? Calorimeter. So this is calorimeter, or rather I may, instead of saying MC delta T, I can say that the heat gained by calorimeter, that's equal to MC into here the change in temperature, we don't say T2 minus T1, we say T1 minus T2 because it's loss. So it is 82.6 minus 47.8. This is of B. So net, you will substituting those values, you will get delta Q gained by calorimeter is equal to M is 40 grams into 1 calorie per gram Kelvin into this one would be 0.8 and 34.8 and minus, we can bring this quantity to the other side, minus 40 into 40 grams into 1 calorie per gram Kelvin into 22.2. So that's equal to 12.6, 40 into 12.6 calorie, or in other words, this would be 504 calorie. So that is the amount of heat gain. So now let's look at the calorimeter. So the calorimeter vessel, we don't know what, it's a very complex vessel. So we can, it has a wool outside and so on. It's made of copper, or maybe it's made of some alloys, we don't know really. Now if you look at it, this calorimeter delta T, the change in the temperature of calorimeter was 47.8 minus 25.6, and that is 22.2. And the amount of energy it gained in the process of that increase in temperature is 504 calorie. Now we introduce a new term called heat capacity. The heat capacity, and which there is no specific here. There's no specific, it's just a heat capacity, is equal to delta Q gained by delta T, and that will be 504 calorie divided by 22.2. Either since delta T you can say degrees Celsius or Kelvin, doesn't matter. I can say Kelvin, and that will be equal to 504 divided by 22.2. 22.2 is equal to 22.7 calorie per Kelvin. So this is the amount of, this is the heat capacity for the vessel, and this heat capacity is a constant for a type of vessel or calorimeter. Now in the next video we are going to use this constant heat capacity, this constant value, and try to better our prediction. So we will try to do a similar experiment with the same calorimeter and use this value of heat capacity. It's worth remembering that the specific heat capacity, this is usually of a material, and this is usually of a vessel or a container or a calorimeter. So specific heat capacity is delta Q, you can say gained or lost, divided by mass into delta T. That means that, for example, by definition, it's 1 calorie per 1 gram for 1 Kelvin rise of temperature for water. So this is a specific heat capacity. For copper, it's 0.095 calorie per gram per Kelvin. So this is for copper. Ice, it is 0.5 calorie per 1 gram per 1 Kelvin. This is for ice. So that's the difference between your specific heat and heat capacity, where heat capacity is only dealing with delta Q over delta T. We don't care about the mass, about how the calorimeter is made, what material and what is the weight and all those stuff. We just worry about delta Q for 1 Kelvin rise. What is the delta Q? And this is 22.7 for this calorimeter. Okay, let's do a quick set of checkpoint questions before we wind this up. So here are the checkpoint questions. Please try to do them, and if you get stuck, please watch the video again. See you until the next one. Bye.